The title of this lecture is Galois Correspondence. And you might find that to be a very unusual name because you've probably heard the name of Galois before and you think of that name as being associated with something to do in algebra and polynomials and equations and things like that. But I want to give you the reason for the choice of this title is there's this problem. So there's this problem in algebra, and that problem is finding what is known as intermediate fields. Now, I assume that the audience knows what a field is. A field is similar to a group, except in a group you just have one operation, and in a field you have two operations. You call one addition and multiplication. And let's say you have Q. This is an example of a field. There's addition and multiplication. And then you have Q adjoin square root of 2 and square root of 3. So this would just mean that it's all numbers that are rational, and you also allow combinations of these two. So for instance, you can have like 3 plus square root of 2. You can have a half plus a third square root of 3. Then you can have, let's say, square root of 2 minus square root of 3, and so on, all different combinations. Of course, if you multiply square root of 2 twice, you get 2. And if you divide square root of 2 by square root of 3, then you get square root of 2/3. So square root of 2/3 will be in this field, and so on. It's similar to when you're using the imaginary unit, but you just have these two extra numbers that you attach to square root. And intermediate fields are the fields that sit in between. So you have Q, you have this. What sits in between? Now, one thing that comes to mind, of course, is what if you just adjoin square root of 2? That clearly sits in between these two. Another one that also works is square root of 3. Though one thing that's actually not immediately obvious is, why are these different? I mean, you cannot just say because you have a 2 over here and you have a 3. For instance, Q2 square root of 2 and Q square root of 2, these are actually equal. And the reason for this is if you multiply this by a half, which is a rational number, it will give you square root of 2. So it does take an argument. Like, it's not immediately clear why these are distinct. And you might say these are the only intermediate fields, but there's actually another one, and that would be Q square root of 6. This is something that you might miss, and these are distinct. And then you can ask the question, how do you know that these are the only three? How do you know there's nothing else? And that's not quite clear how to do it. And in algebra, we talk about what is known as Galois correspondence. The way Galois correspondence works is, let's say we call this one F, that's our field, and let's say we call this one E, that's our other field. Then you create something called the Galois group, And this is a group, and amazingly, the intermediate fields are determined by subgroups. Let's call this G, subgroups of G. So this is the amazing relationship that you took a problem that is a problem among fields and you converted it. So once you calculate the Galois group, whatever that means, which we're not going to talk about because this is not an algebra class, but maybe some of you have seen it. And if you've never seen it before, this is just a quick prelude to what lies ahead. You calculate this thing known as the Galois group between these two fields. So once you can calculate what it is, you can then determine its subgroups. And the subgroups will tell you all of the fields that sit in between. And this is an amazing correspondence because it converts one type of problem into another type of problem. But we're doing topology. And amazingly, in topology, we're going to have something very similar. But we're going to do this with covering spaces. And in fact, I would say that our correspondence that we're about to show is perhaps even more surprising because Galois correspondence in algebra, after all, converts one type of algebra into another type of algebra problem. But what we're about to do is you're taking a problem in topology and you're converting it to an algebra problem. So those are more further apart from each other. So I think this is a more surprising correspondence. But let's see how this works. So we're going to let Y be a space, topological space. and we pick a base point in Y. So every time we write a space, we assume the usual hypotheses that we've been using, that it's path connected and all of that kind of stuff, which is going to be applicable for the kind of spaces that one encounters in topology anyway. And this might bother you a little bit. Why do we have to select the base point? This is just because when we work with the fundamental group, there's always a base point that you have to choose where to calculate the fundamental group. It really does not matter which one you pick because they're all isomorphic, but it's just that the way the definitions are set up, you have to insist on where you want to begin. Also, as we've seen many times before, when you lift the path into the cover, you need that initial condition. Otherwise, there's lots of paths you can lift it to, but when you specify what the initial point is, then you get that unique lifting. So that's another reason for why it comes up. You just have to naturally put it in there so that the decisions that you make along the way become uniquely defined. Obviously, it does not matter what the point is. You just that's just a requirement in the definitions and in the theorems. And you pick a point, and what we want to do is we want to determine. So recall the category that we introduced. It's called the covering category. Cover y, y0. So the objects. So the objects of this category are going to be triples x, comma, x0, comma, pi, where pi is a covering map from x to y, and it sends this is a initial condition to that initial condition. So it's coverings where, and maybe you can add pi as a covering. Is a covering. So pi is going to be a covering, and so we have a covering map, we have this initial condition, and these are going to be the objects. And what are the morphisms? The morphisms, so these are, the morphisms of this category. So a morphism takes place between two objects. So a morphism of this category, so we need two objects between, so let's say one object is x, x0 pi, and the other object is x prime, x0 prime, pi prime, is a continuous map. Let's not even give it a name, from x to x prime, so that the following diagram commutes. X, x0 gets mapped to x prime, x0 prime. But x and x0 and x prime and x0 prime, they are both coverings of this space that we picked in the beginning. So that would be a morphism in this category. And we would say, and then we say that two coverings are, let's say, isomorphic when this morphism is an isomorphism, or maybe you can say a homeomorphism. So that's what it would mean, a morphism. So this morphism is an isomorphism. So the topological spaces are homeomorphic to each other, and they're compatible with these maps. So all you're saying is it's the exact same covering, just written out in a different notation or a different language, pretty much. But fundamentally, it's the same thing. So we're going to be interested in determining all objects. So this is what we want to do. We want to determine, so our problem is going to be this, is we want to determine all objects of the covering, all coverings of that. And obviously, there's an infinite number of objects, but most of them will be isomorphic. So we say non-isomorphic. So, or you can say distinct, things that are actually different. So the ones that are like fundamentally different types of coverings for that space. And this is the part that's going to be amazing. So this is the amazing solution. This is the solution. You're going to compute the fundamental group of that space, right? So this is the the fundamental group. Not the Galois group, but it's the fundamental group. And this is the amazing answer. So the coverings of y0 are determined by the subgroups. Of the fundamental group. So this is the amazing answer, that once you can find what the fundamental group is, assuming you can find it, sometimes it's not easy to find, but assuming you can find it. So once you find the fundamental group, you're going to look at the subgroups, assuming you can find the subgroups, because that, of course, if the group is very complicated, there might be lots of them, but assuming you can find the subgroups, then the subgroups will tell you all the kinds of coverings you have, and that's the simple answer. And then what we're going to do in this lecture is we're going to say more accurately what the theorem is. We'll show an interesting example that shows you how it is used, and then we'll give a proof of this. But before we do anything, it would be helpful to recall some facts about the fundamental group that we talked about before, but we're going to have to use it again. So let's start with that first. Let's recall this fact again. We mentioned it before, but we'll be using it, so it makes sense to go over it. So let's say that we have a covering. Is a covering. We get something called the induced map. We get the induced, maybe we can call it homomorphism, on fundamental groups. So you call it pi star because it comes from the original covering map. And this is going to be a homomorphism on fundamental groups, x0 to y0. So that's the induced homomorphism. And how is it defined? Well, it's defined very simply that, recall what the fundamental group is. The fundamental group is the group of all loops at x0. Technically homotopy classes of loops, but that's too much to say. So I'll just be a little bit sloppy and I'll just say loops. And the way it works is that if you take a loop, so let's say you have f is a loop, so f is just a mapping into x with f of 0 is equal to f of 1 is equal to x0. So it's a mapping, so it's a loop. The way you get a loop in the cover is you project it. So you use the covering pi to project it down. So you will get pi composed f. And this will, of course, now be a mapping from 0, 1 into y, because f takes you from the interval to x, and pi will take you from x down to y. And because the base point goes to that base point, this will be a loop in the base. So if you want to just see like a picture of this, we often envision a covering as a stack of pancakes, though it's not really the best picture because this is a path disconnected space, but let's not worry about it. And then this is pi, and this is our cover, right? So this is this entire thing. This is what we're calling this is what we're calling x. So this thing over here, this is what we're calling y. And the idea is that if you have some kind of path, and then you're just projecting it down. So you take a loop and you project it down. So this is what we call the induced homomorphism. You actually have an induced homomorphism for any continuous mapping, not just a covering. But when you have a covering, you have a special property. So we have the property that pi star is an injection. This is an injective mapping. In general, if you just have a continuous mapping between topological spaces, as we've said, if this is an injective mapping, the induced mapping does not need to be injective. If this is a surjective mapping, the induced mapping does not need to be surjective. In this situation, it's a little bit funny because the covering mapping it's a surjective mapping, but the induced mapping becomes injective. It might sound funny that it happens like that, but that's just the way it works out. So pi star is an injection of this into that. And the reason for this is actually quite simple, because if let's say pi star of one loop is equal to pi star of f2. Now when we write equal to, really we mean homotopic to, because we're not really talking about paths, we're talking about homotopy classes of paths. So if they're homotopic to each other, that would mean their projections are homotopic. Their projections are homotopic. But then that would imply that the original paths must be homotopic, and this is because of something that we talked about, homotopy lifting. That a homotopy in the base lifts to a homotopy in the cover. So these are the projected ones, but when you lift them, you get back the original path. So this is the original loop. That's the original loop. So these are now equal, well, homotopic in the cover. So that's the observation here. And so we abuse notation. And we would write that the fundamental group of the covering space is a subgroup of the fundamental group of the base. That's what we would say. It's kind of similar to when you say that the integers are a subset of Q. I mean, they're not really a subset of Q because Q contains pairs. It's like fractions, and these are just integers. But what we mean is that every integer n can be mapped to a rational number n divided by 1. And this assignment, it's an injection. So that's really what we mean. So we just abuse notation, and we say Z is a subset of Q because there's no ambiguity. When you write two distinct integers, they are distinct rational numbers. So there's no ambiguity when you write them. So in a very similar way, we would say that this is a subgroup of that, even though it's not really a subgroup, but this is just convenient to write. Now, let me also perhaps would say this. Let's make this a little bit more precise. So let us say a bit more precisely what it means for, so let's say we pick a loop in Y. Again, it's really a homotopy class. If I want to be more careful, it's really a homotopy class, but I want to keep the notation simple. So let's say we pick a loop. I want to say a bit more accurately what it means for a loop in the base to also belong to the cover. Right, we're saying, so we're being sloppy. This is not actually correct. Rather, more accurately is we're saying one can be injected into the other. So if we're being sloppy and we're saying that this is a subgroup of that, then it would mean that some of the elements here are also elements over here. Like, for example, maybe to make it a little bit easier for you, like we would say that 5, like we would say, for instance, 10 over 2 is an element of Z, right? We would say 10 over 2 belongs to the integers. Now, it does not really belong to the integers. It's a rational number, but what we mean is 10 over 2 is equivalent to 5 over 1, right? Because Q is really equivalence classes of these fractions. So it's 5 over 1, and then 5 over 1, and then you could map 5 into 5 over 1, which is 10 over 2. So you can find 10 over 2 comes from an image of Z. So, but we write 10 over 2 belongs to Z. So in the exact same way, let's be a little bit more specific, a little bit more careful about what we mean for something in this group to also be an element in this one. Well, you could say that there's something in the cover that projects to that, but I think what would be helpful is to realize that what this means. So when I write this, what am I referring to? I'm referring to this. What does it mean for a loop in the base to belong to the cover? So what this means is that F lifts to a loop in the cover. In general, and we've talked about this many times before, is if you pick a loop in the base, maybe I should write it here. In general, loops in the base lift to paths in the cover. In general, they will not be loops. The endpoints might become separated, as we saw many, many times before. But when you're saying that a loop is also a loop in the cover, it means that that particular loop, it lifts, when you lift it to the cover, it will lift to a loop. It will stay a loop in the cover. And the reason for this is because what this really means is that there's something in the cover, there's something in this group that projects to that. But if it's coming from this group, then by definition it means it's a loop at x0, right? So therefore this loop remains a loop when you lift it to the cover. Okay, so we have this, and I wanted to mention something quite interesting. So this is, let's write this down as a proposition. Let pi from y0, I already messed that up, from x0 to y0 be a covering. So then the number of sheets in the covering is equal to the number of cosets of pi1 x0 in pi1 y0. So I'll explain to you what this means if you need a reminder. But going back to what we said, when we have a covering, the fundamental group of the cover is a subgroup of the fundamental group of the base. So you can talk about the cosets. This is a subgroup of that, so you can talk about the cosets. The cosets, this is if you quotient, so if you quotient the group by its subgroup, and you count, right? You count how many you have. This is also called the index of the subgroup in the group. And the notation that sometimes people use is you put the group first. That's the way people write it. And then you put a colon, and then you write the subgroup. So these are just different ways to say it. I think maybe we should just recall what we mean by coset. So just all it means is, I'll write it right over here. So let G be a group. So this is a group in general. Forget about topology. And H is a subgroup of G. Then G mod H. So this is what we call the cosets of H. This is equal to, by definition, you're going to just take, this is going to be H, and then you're going to look at all translates of H. You're going to just multiply them by something in the group. So basically, you would, if you want, you can say that these are translates of H. You take the subgroup and you multiply it by an element of the group, so that means you just translate the entire subgroup. Again, when I say translate, I'm just using the picture of moving things around by a translation, but of course, in the abstract, it does not necessarily look like anything. And it's very similar to when we talk about a topological space being quotient by a group. It's similar, but it's a little bit different here, of course. But it's a very similar analogy. And of course, it could happen that maybe you have two different elements of G that give you the same translate. So then you would say those two elements, like it could happen, for instance, that maybe GH is equal to G prime H. So just because you have distinct elements of G does not mean that these translates are distinct. But that's what we call the cosets. So that's the proposition. So this is quite interesting, that the number of sheets, this is a topological result, and it's connected to algebra, that this is a subgroup, the fundamental group of this is a subgroup of the fundamental group of that, and the number of cosets that you get is the number of sheets. So let me give you a proof of this. And to save time, this will be a partial proof. I'll give you like the main idea, and there'll be a small step that you have to put in yourself. So this is a proof. There's going to be one small little detail missing. So here's the way we do it. Maybe a picture would be helpful. So I'll draw a picture right here. Let's say this square represents y, and this is y0. And then this, and when you pull back y, you have, so these are the fibers. I'm sorry, this is the fiber. This would be pi inverse of y0. So this is the fiber over y0. So all of them are being mapped to y0 using the covering. And one of these fibers, one of the points in that fiber is going to be x0. Right? One of them is going to be x0. And then you can have other ones. So let's say you have another one over here, x. So what we say is for each x in the fiber over y0, we're going to pick a path. And let's call this path fx. So we're going to pick a path from x0 to x. It does not matter how you make the, you're just picking a path. So this is a path from 0, 1 into x with, that starts at x0 and it ends at x. So that's what you're doing. For every point in the fiber, you're going to create a path. The path will begin at x0, so you'll have a loop from x to itself. Then you'll have a path to this one. Then you'll have a path to that one. And you'll have a path to that one. You'll have a path. So for every point in the fiber, you create a path. So you have lots of paths. And we argue that if you take this subgroup, so if you take pi 1, well, let me say it like this. We have that. Let me remove this. And now observe that if you project these paths, so if you do pi composed fx, are all loops at x0 in the base. And this should not be x0, this should be y0. So this path over here, because these get mapped to the same point, you end up getting some kind of loop. Right? It gives you some kind of loop. So you just got loops in y. So thus, pi composed fx, they're all elements of the fundamental group of y at y0, because the fundamental group, by definition, it's loops at y0. Technically homotopy classes, but I do not want on saying path homotopy classes. And we claim that this collection, pi composed fx, so that collection, so this is a set of loops where x ranges over the points in the fiber, are all distinct mod this subgroup. They're all distinct mod the subgroup. So in other words, what do we mean? What we mean is, i.e., if x is not equal to x prime, and these are two points in the fiber, then this translate of this subgroup and this translate of this subgroup, that they're not different. Right? So just maybe to clarify, how do you get the cosets? You have a group and you have a subgroup. The group here, that's pi 1 y y0. and the subgroup is pi1x, x0. And these g's are coming from the fundamental group of y. So you're just translating the subgroup by all of them. And those are called the translates. And we want to show that they're going to be different. That's what we're trying to argue here. So this is like your subgroup H. This is something in the group, and you're just translating the subgroup by that element, and you're doing this over here as well. And you're saying that these are going to be different from each other. And, well, how would you prove this? Well, if they're the same, then that would mean that this is congruent to that mod the subgroup. So then pi fx. So suppose, so let me just say like this, let's maybe do it by contradiction. So suppose they are equal. So then pi fx would be congruent to pi fx prime mod this subgroup. Hence, pi composed fx would be equal to pi composed fx prime, and then multiplied. And multiplication in the fundamental group is the juxtaposition. That's when you put one path next to another path. So multiplied, so juxtaposition, by something in the, so let's call it f, for some f in here. And now we're going to take this, and equal, of course, means path homotopic, of course, but we're being sloppy. And now you're going to lift this. So if you lift, this is the projected loop, so it lifts to fx, and you're saying that this is going to be homotopic. This one lifts to fx prime, juxtapose, and this f lifts to, whatever it lifts to is going to be a loop. The reason for this is what we said earlier, that if an element, if a loop in the base belongs to, it comes from the fundamental group of the cover, then when you lift it into the cover, it will remain a loop. So this is going to be a loop. And this is impossible. So this homotopy is impossible unless x is equal to x prime. Because what are we saying? What is this? This is a path. By definition, this is a path from x0 to x. And this is a path from x0 to x prime. But we're saying that at x prime, so you have x to x prime, and then you juxtapose it with a loop at wherever that is, right? So you're going to just juxtapose it by a loop. And this is where we have a problem. How can these be path homotopic? This does not make sense. How can these be path homotopic to each other? So, you know, if they're path homotopic, then that means there has to be something, right? This is where it's a problem, because this one lifts to a loop. And so you have an issue that this whole thing is homotopic to that one, even though the endpoints are different. So this is where you have a problem. So what does this show? So hence, this collection of loops, pi composed fx, as x ranges over the fiber, are all distinct mod the subgroup. Therefore, if you look at the coset, so if you take your group mod the subgroup, has at least, so you're going to look at this fiber and you're going to count it, at least that many cosets. Because we've just produced a collection of elements of the group that are different mod the subgroup. How many do you have in here? Well, you have one for every point in the fiber. So you have at least that many. And to complete the argument, right? So to complete to complete the proof, you need to show maybe at most that number. So that's like the second half of the proof. And then that would mean that the exact number is equal to the number of cosets. So I'll just stop it here because I think I already gave you the most important idea in this argument. But this is a really nice result, that the number of sheets, this is topological, and the number of cosets is algebraic. And we have this nice relationship between algebra and topology. And now we're going to get to how you determine the coverings, all of the coverings of a topological space. We are going to classify coverings in a special case. The general case will actually be somewhat similar, but I specifically want to do something that we're comfortable with. So we're going to talk about classification of coverings in a special case. So this is going to be the special case. We're going to assume that X is simply connected, and G is going to be a subgroup of automorphisms that acts evenly on X. And what we will do is we will classify all coverings of, maybe we need to pick a base point as we usually do, so let's just put it in here. We're going to pick an x0 in X, and x0 bar, that's going to be something in the quotient. So this is just the class of x0 mod G. We're going to classify all coverings of X mod G with this base point. So you see, we're saying special case. So the special case here is referring to when the base is a quotient by some group. It's a quotient of a simply connected space by some group. The general case, where the base is an arbitrary topological space, can actually be reduced back to the special case. I just want to talk about the special case because this is something we've talked about many times before, and this is what you are comfortable with, what you're more comfortable with. And this special case is quite general enough, actually. So it probably makes sense to not overcomplicate it and just assume that this is our base. So we're going to classify all coverings. And here is what you should notice, is that if, so you're going to observe that if some new space, let's call it Z comma Z0 X mod G, is a covering, then the fundamental group of the covering is a subgroup of the fundamental group of the base, as we've said before. But the fundamental group of the base is isomorphic to the group of automorphisms. And thus, the fundamental group of the covering corresponds to some subgroup of G. Right? I do not want to say it is a subgroup of G because technically, if you want to be super precise, it's not a subgroup. This is, it's not even a subgroup of that. It gets mapped to a subgroup, and then you have this isomorphism here, and whatever subgroup this corresponds to here is then mapped isomorphically to some subgroup over here. So in the end, this corresponds to some subgroup of G. Okay, so what we see is if you have a covering, that covering can be mapped, can be sent to a subgroup of G. So coverings correspond to subgroups of G. But then you can go backwards. You can now reverse the process and you can go backwards. If you have a subgroup of G, you can create a covering out of that. So let's show how you would go backwards. So conversely, if H is a subgroup of G, then H also acts evenly on X. I leave that for you to think about. That's just should be like a 1 or 2 liner. What does it mean to act evenly? It basically means that if there's a small enough open set that if you move it around using the translates of G, they do not overlap. Well, if you move around them using the translates of H, there's even fewer of them, so they certainly do not overlap. So therefore, X mod H is a covering. So if you're confused by what that means, it means exactly what you think it means. An element in this quotient, it's some point in X, but it's the translates of X mod H. So we could just call it X bar. That's the translates mod H. And you're just mapping that to X bar. These are the translates mod G. So it looks like it's the inclusion mapping, but it is not. This is classes mod H. This is classes mod G. This is a covering. It's not difficult to check this. You basically have the following diagram. You have X. So this is a covering. So this is a covering because H acts evenly on X. So the map from the simply connected space to the quotient is a covering. Then you have a covering like this. That's a covering. And now you have this. You have a mapping. This diagram commutes because quite simply X gets mapped to X bar, and this X gets mapped to X bar. These are just X mod H, X mod G. But you can see that going like this and going like this. So this diagram commutes, and it takes a bit of an argument. It's not difficult to show that this is a covering, that this is going to be a covering. You have to be careful. The arrow has to go from here to there, because if two things are equal to mod H, then they're certainly equal to mod G. It's not true the other way around. Going the other way around, you would have a problem because the map would not be well defined. But going this way, the map is well defined. So that's the correct way to write it. So thus, X mod H, let's include the base point here. X mod G is a covering, and the number of sheets is equal to the index of H in G. That's the way you write it. So how many cosets you have, that would be the number of sheets for the covering. So this is what we're saying. If you have a covering, that covering gives you a subgroup. Likewise, if you have a subgroup, that subgroup can be used to create a covering. But the question that arises, and this is perhaps the most serious question, it's basically this. Is it true that this is like a one-to-one relationship? Is it true that a covering is completely determined by its corresponding subgroup of G? So that's really like the main question. And this is what we're going to prove. So I would say this is the main theorem of the lecture, and it's going to be this. So let X be simply connected, and let's say we pick a base point, and G be a group of automorphisms which acts evenly on X. And suppose we have a covering pi. Instead of calling it Z, let me call it Y, and I hope this does not bother people, because I know that previously when I used the notation, Y was the base and now it's the cover, but hopefully that's not a problem. So suppose this is a covering, and the fundamental group of the covering corresponds to H, to some subgroup of G, where G is the group that's isomorphic to the subgroup of the base. So this is the base. So as we remarked before, that the fundamental group of the base is isomorphic to G, and let's say, and the fundamental group of the cover, it's a subgroup of the fundamental group of the base, so therefore it corresponds to some G. And let's say it corresponds to some subgroup of G. Let's call it H. So then there is a homeomorphism. So there's going to be the following homeomorphism. So we have X mod H, X0, going to Y, Y0. We have pi going to the base. And then we have a covering going like this. So then there's a homeomorphism between these two, which makes the diagram commute, which makes the diagram commute. So essentially what we're saying is, so basically this covering is the same thing as this covering. Basically, it's just written in a different language, different notation, but it's the same thing. And so what you see from this theorem is all coverings of this base are determined by subgroups, of this G. So that's really like the main theorem that we want to get to. Before we prove this theorem, I would like to go over an example that illustrates how this works. But it would be helpful to maybe talk about this isomorphism over here. So let's maybe say something about this isomorphism. How does it work? We talked about this before, but I want to go over this part again. That if I give you a translation in this group, and again, when I say a translation, it's not necessarily a translation. It's just some kind of automorphism of your space, but we just visualize it as a translation of X. If I give you a translation, how do you, so it's isomorphic, so that means it gets mapped to some loop. So how do you get a loop out of this? Well, the way you do it is you start with the base point. So you start with X0, and you take, so let's say that G is an element of the group, so it's some kind of translation. And when you apply this translation to X0, you get a new point, right? So you get some kind of new point. And then you're going to create a path from X0 to G of X0. Let's call this F. So you're going to choose a path F from X0 to the translated point, G of X0. Then, if you project down to the quotient, so then F bar is a path from X0 to itself, because the translated point, it's in the same class mod G. So this is a loop. And so when you project it, you get a loop in the, so you're getting a loop in the quotient. So you're getting something in the fundamental group. So this is the way the isomorphism works. So given a translation, you take your initial point, you translate it using this G, you draw a loop, you draw a path in the simply connected space, and then you project that path down to the quotient and you get a loop. Because you're in a simply connected space, it does not matter how you draw the path, because they will all be homotopic to each other since it's a simply connected space. So that's the explanation for how this isomorphism works. And now I would like to show you an example. So this example is, we're going to classify all coverings of the circle. And we're going to choose some base point. And the way we solve this is you're going to take advantage. So we're going to let X be the real line. And G, this is going to be the group of integer translations of, so these are integer translations of X. We're going to choose a base point. Our base point is going to be 0. And then we have to observe that if you do X mod G, then this is homeomorphic to a circle. So we're just replacing the circle by a quotient, and we're going to solve the problem for the quotient. And now, so we know that the fundamental group of the quotient at that base point is isomorphic to the group of translations. Okay, and the group of translations is, of course, isomorphic to the integers. So the subgroups of the integers will give you the coverings. So here's how you do this. So now all subgroups of the integers have the form that it's some multiple. Let's say it's nz for some non-negative integer. So if n is equal to 0, those are the 0 multiple, so that's just a trivial subgroup. And if n is equal to 1, then that's the entire group. And if n is 2, those are the even integers, and so on. So that's how all of the subgroups are determined. There's no need to use negative integers, because negative nz and nz will be the same subgroup. So these are the subgroups of z. So let's do it for a specific example. So let us illustrate this for the subgroup 3z. And we'll understand how this works. So we have okay. So let's say let H, so this is going to be a subgroup of G, and H, these are going to be translations by multiples of 3, right? Multiples of 3. So that's going to be this. This is all integer translations, and these are translations by 3. We get a covering. So this is the covering that we get. If we take the real line, so that's our simply connected space, and we quotient by H, then we get a covering to the real line quotiented by G. And the mapping here is actually quite simple, that x bar, and this just represents a real number mod H, is getting mapped to x bar. But we write x bar again, but this time x bar means this is the class mod G. Now, this is not very convenient notation. It's more convenient when you write it back in terms of the circle. So we're going to use this isomorphism, this homeomorphism with the circle. Now this is homeomorphic to the circle. So this one is homeomorphic to the circle. And this one is also homeomorphic to the circle. So let me just maybe explain that part if you're confused by this, because these are, so G represents translations by integers. So if you draw the real line, you have 0 and you have its translations. And they repeat. So if you confine yourself to that interval, then if you take any point on the real line and you consider its class, it's going to be, you can always be brought back to this interval. So you have this interval, but the endpoints get glued together, and by gluing them together, you end up getting the circle. So that's the reason why there's a isomorphism from this one with the circle. And the isomorphism goes like this. You just take x bar and you map it to e to the 2 pi I x. So that's the isomorphism with the circle. Notice that it's periodic by one integer, because if you take this x and you shift it over by 1, you're just replacing x by x plus 1, but this function is periodic, and so it gives you the same point, which it's supposed to. So this is your homeomorphism. And you actually have something very similar with this circle, but the homeomorphism is just going to be a little bit different, because this is the translations by multiples of 3. So then the picture will go a little bit differently this time, that you would have your real line, you have 0, and then you have its translation. So you have 3, 6, and so on. You have -3, -6, and so on. And then you realize that just like before, everything is really determined by what happens on that interval, that if you have a representative that is outside that interval, it can be translated back to be between 0 and 3, and then 0 and 3 get identified, and you end up getting the circle. So this isomorphism that we're getting, what it does is it takes x, it takes this class mod h, and what does it send it to? Well, here you have to be a little bit careful. It actually goes to e to the 2 pi I x over 3. So it has to be x over 3 because it has to repeat every 3. So that's the reason why it's written like this. So this is the homeomorphism from that quotient with the circle. Now, we can therefore convert, this is a covering, and now we just convert it to this notation so that the diagram commutes. So therefore, what is the correct mapping from the circle to the circle that will make this diagram commute? That mapping is, notice what you're doing, this is 2 pi I x over 3, and this is 2 pi I x. So the correct mapping from the circle to the circle is you take your complex number z, and you just cube it, it's z cubed. So in the notation of the circle, you're just mapping the circle to itself by using the cubing map. So the subgroups that are nz, if n is a positive integer, it just corresponds to this z to the n map. Of course, if n is equal to 0, then that corresponds to the trivial group, which in the end just will correspond to the universal cover, right? That's the extreme case. But this is the way that it works, you get these coverings. And I just want to maybe go over this isomorphism, just a separate example, because it's going to come up in the proof again. So I'll take this down. Right, so I'll take this down. Maybe I can summarize what we've shown. So the coverings of the circle are all given by, so you could map the circle to itself by the mapping z to the n, and this is for n is equal to 1, 2, 3, and so on. And you can also map, and the other exception, this is basically the extreme case, this is when you map the real line to the circle, and this is the exponential map, as we've talked about. So this is the complete classifications of all coverings of the circle, because the covering of the circle is isomorphic to the integers, so the subgroups of the integers will correspond to all of those coverings. And the classification theorem says that this is the complete list of all coverings. Any other covering that you can possibly come up of the circle will have to be isomorphic to one of these two, either this one or that one. Well, actually, there's an infinite collection of it. These are these are sheets n, this is infinite sheeted. But that's the way this works. And it kind of makes sense, right? The z to the cube map, it's a 3-sheeted covering, and the cosets, if you do z mod 3z, you get integers mod 3. There's 3 classes mod 3, so it's a 3-sheeted covering. So the amazing thing about this is a complete classification. Any other covering will have to be isomorphic to these. So now, of course, you can come up with silly examples, and by silly examples, I mean you can take 2 disjoint circles and map it to one circle where this is, let's say, z squared and this is z cubed. But we're not allowing things like this because this is a path disconnected space. But it would be a covering, but it's just a path disconnected space. So based on our assumptions that we have been doing up to this point, this will be a complete classification of all coverings of the circle, which is a non-trivial result. That it's interesting that we can find all of them. And before we go on to prove the theorem, it would be helpful to recall how this isomorphism works. So we're saying that the fundamental group of the circle is isomorphic to G. So that means there's an isomorphism map from this one over here. And the way it works is, this is what we were saying, pick some translation. So we're going to pick, so let's say we pick translation by 3 in G. And since our initial condition is 0 on the real line, if you apply this translation to 0, you get 3 on the real line. So you have the real line, you have 0, you have 3, and now you just pick any path. So now construct the path from 0, 1 into the real line. F of t is 3t. So 3t would be the map. It starts at 0, it finishes at 3. If we project, and then we have the universal cover from R to the circle, this is the exponential map. So then if you project, if you use the universal cover, exp of 3t, you end up getting e to the 2 pi I t. I'm sorry, 2 pi I 3t. and this is a mapping from 0, 1 into the circle. And this is the path that winds around 3 times around the circle. And this just example quickly illustrates how this isomorphism works, that the way you get a loop, in the way you end up getting a loop in the fundamental group is you take your initial condition, you apply the translation, you move it to a new position, you draw a path between those 2 points, and when you project that path back down using your covering, then you end up getting a loop in the fundamental group. So this example illustrates how the classification theorem works and how this isomorphism works. I know we talked about this isomorphism before, but it would be helpful to recall it again as we prove the theorem. And now we'll get to the proof of this theorem. So let's take this down and we'll carefully discuss how this theorem is proven. Let's write down the theorem. We're going to assume X is simply connected. And we're going to pick some kind of initial condition in X. And then we're going to assume that G is an automorphism group that acts evenly on X. And we're going to say that suppose pi is a covering from some space y, y0 to X mod G is a covering map and let's say that the fundamental group of y, y0, which is a subgroup of the fundamental group of the quotient, and the fundamental group of the quotient is isomorphic to G, corresponds to the subgroup H. So again, whenever you have a covering map, the fundamental group of the cover is a subgroup of the base, but the base happens to be isomorphic with G. And so this group, under this isomorphism, it corresponds to some subgroup. So let's say it corresponds to H. Then, if we do X mod H, then this mapping is a covering mapping, is a covering, and there is a homeomorphism between them. So there's a homeomorphism from this cover to the Y cover that makes this diagram commute. So there's this homeomorphism, and when you have this homeomorphism, what it basically says is this covering is essentially the exact same thing as that covering. And so you do not have any new coverings. All of the coverings are determined by the subgroups of the automorphism group. So let's go ahead and prove this. So here's proof. Now, what I'm going to do is I'm going to first give you the short proof that is going to overlook a detail, which is the most difficult detail in the proof. We're going to overlook the detail, and then we're going to return back to the detail, and we'll fill in that detail and explain why it works. So here's what it has to do with. So this is skipping that detail at first. I'll make it easier to understand what we're doing. That we're going to say that since x0 is a covering, and X is simply connected, this covering is the universal covering. So universal in the sense is, i.e., x0 is the initial object among all coverings of this space. And because it is an initial covering, there's a unique, so what does it mean to be an initial object? It means there's a unique, so thus there is a unique morphism, let's call it alpha, from x to y, such that the following diagram commutes. And that diagram would be this. So you have x, x0. This is a covering of the quotient. And then we have another covering by this space, y, y0. So because x is a simply connected covering, it is the initial object among all coverings. And so there's a unique morphism that makes this diagram commute. This is our previous lecture when we talked about universal coverings. When does a space have a universal covering? And we said that if a space has a simply connected covering, then the simply connected covering will be the universal covering. So in other words, the initial object. So there is a unique morphism that makes this diagram commute. And it turns out that alpha induces a mapping on the quotient. So from x mod h into y. By the rule, so I'm going to abuse notation. I'm going to call this alpha and I'm going to call that alpha. You technically have two different alphas. So maybe you can call this like alpha bar or something like that. But I'm just going to abuse notation. I'm going to call both of them alpha, and we are mature enough to understand which alpha is referring to which one. I just want to use the same symbol because we're constructing a new map by using an old map. And basically, it's the exact same mapping, but it's being done on classes. You're going to pick a class mod h, and you're going to define alpha of this class is just alpha of x. Now, there is a question, of course, is this well defined? So that's really the big question. Is this actually well defined? Because when you define alpha on the class, you're choosing a representative for that class. What if you have a different representative? How do you know you end up in why the answer will turn out being the same? So it does have to be justified. But for the moment, let us accept that this is true. So if we're willing to accept that this is true, so if we're willing to accept that this is true, and when I say this is true, I'm referring to the fact that alpha is well defined on the quotient, then we get the following commutative diagram, x mod h into this. So this is, of course, so this mapping, this is just the mapping that maps a class mod h to a class mod g. Then this diagram commutes. And the reason why this diagram commutes is very simple. I mean, you can just work this out. If you have a class x, this class is being mapped to alpha of x. You just choose a representative and you use the old map. And this map going like this, that's just x bar again. And it's compatible because you see it has to do with the fact that this is commutative. If you pick an x, it gets sent to x bar, right? It gets sent to x bar, which is the same thing as going by alpha and then pi. So this diagram commutes simply because the original one commutes. So you have a commutative diagram, and also this is going to be a continuous mapping for the very simple reason because this is a continuous mapping. So everything here kind of works out. So then this diagram is commutative. And then we can add furthermore, this mapping alpha from this quotient to this space is a covering map. We've seen this before, and you had a problem like this on your homework. It basically has to do with the fact that this arrow is a covering map and this arrow is a covering map, and then you can work through this and show that this one has to be a covering map. It's not particularly that difficult, but you actually have a covering. So this is a covering. So this is a covering of Y. Now, look at what we have. So now observe that the fundamental group of the quotient, so this fundamental group is, so because this is a covering, the fundamental group of this is a subgroup of the fundamental group of this. But the fundamental group of Y is what we're assuming. This is the one that is homeomorphic to H. That's the one, right? This is the one that we said is homeomorphic to H. Let me actually go back in the statement of the theorem. You see, in the theorem we said that the fundamental group of Y is a subgroup of the fundamental group of the quotient by G. And this fundamental group is isomorphic to G itself. So the fundamental group of Y corresponds, under this isomorphism, to some subgroup of G. So H, that's the corresponding group over here. And this one, because you're quotient out by H, this one is also isomorphic to H. So they both correspond to the same subgroup. So in particular, if you take the index, so if you take this space and you look at the index, so you count how many cosets you have, this is equal to 1, right? Because this is basically H mod H, a group quotienting out by itself. So that there's only one coset. And the number of cosets is the number of sheets. So thus, alpha is a one-sheeted covering, i.e., that's just another way of saying alpha is a homeomorphism. Because if it's one-sheeted, that means the pre-image of every point, it's just one thing, so it's an injective mapping, and then it's not difficult to show why the inverse is a homeomorphism. So a one-sheeted covering is a homeomorphism. So this proves it. So we've shown what we claimed, that there is a homeomorphism between this covering and this covering. So every covering that you can possibly come up with, a covering of this space, it arises as a quotient by some subgroup of automorphisms. So you have the automorphisms that generate for you the entire group, and if you pick a subgroup of them, that will give you a covering of that space. So that is the collection. That's actually a full description, full classification of all of these coverings. And that's the proof of this, and it's a nice proof, but it uses a lot of the ideas that we talked about before, but we do have to get to the issue of why this alpha map is well defined on the quotient. So that's what we have to get to, and that's really the most technical part of the proof. It feels like this should be the easiest part of the proof, but no, this is actually the most technical part of the proof. So I'm going to leave this up the way that it is, and I think it would be helpful to recall how this alpha map is being defined. And so let's take all of this away and now focus on the other detail showing why alpha is well defined. So as the question is, why is alpha from the quotient this time well defined? So let us first recall how the original alpha map from the universal cover to Y is constructed. So here's a picture. We talked about this in the previous lecture, but you really have to understand this in order to make this work out. So let's see how it is. So we have, basically what we do is, we have a point x0. Okay, so let's maybe say it like this. So we're going to pick x in the universal covering. How do we, so alpha of x has to be something in Y, right? This is a mapping. How is alpha of x defined? How do we create this map? So here's how we do it. We have our initial point x0 in the space, and then we have this x. And we're just going to pick a path. And let's call this path fx, right? So this is what we do. We pick a path fx, and this is a path in x from the initial condition to x. And then what do we do with the path? Then we project. So fx bar is a path in the quotient that starts at x0 bar. You notice that I write a path, I do not write a loop, because this x is an arbitrary point. It's not some translate. It's not a translate by from x0. This is just an arbitrary point, so I'm not saying it is a loop. So you take a path over here and you reduce it mod g. So now you have a path over there, and then you can take this path and you can lift it to y. Then you can lift fx bar to a path, let's call it fx tilde, to a path in y, which starts at y0. And then we set, so how do we define alpha of x? So alpha of x is an equal to, by definition, this is the way we define this alpha map, we just take this path and we look at the terminal point. It's just a terminal point. So that's basically what you do. You take a path in the universal cover, you project it to the quotient, then you lift that path into the covering space y, and then the terminal point, the initial point is going to be y0, but the terminal point of that path, whatever that is, that's a point in y, and that's how you define alpha of x. This is how you map this point to that point, and then by doing so, the diagram will commute, and it's going to be a continuous map and all those things. So that's the way that you do it. And the reason why it's important that x is simply connected, because if you picked a different path, right, if you had a different path over here, then because x is simply connected, there would be a homotopy between these two paths. And that homotopy will project to a homotopy in the quotient. And a homotopy in the quotient will lift to a homotopy in y. And so the final point that you end up getting in y will always be the same. So even though you are making a choice of the initial path, that you're using the kind of path you want to move across, it does not actually affect the way the alpha map is being defined. So even though there's that choice that you make, it does not really matter in the end. So what we have to do next, okay, so that's the idea. So here's what we do next. So to show that alpha from x mod h into y is well defined, we pick 2 points, x and x prime, in the simply connected space, with x and x prime being the same mod this h. So that's another way of saying that x prime is some translate of x for some translate in this subgroup. Okay, now, so here is the picture. We have x0. So let's maybe do it like this. Let's say the square represents the simply connected space, and that's x0. And then you're going to have a path, you're going to have a point x, you're going to pick a path fx. And here you're going to have x prime. Actually, maybe I'll do it the other way around. Maybe I'll call this fx, and I'll call this x prime. Okay, and now the situation is a little bit more complicated, because you have these paths that do not necessarily meet at the same point at the end, because the x and x prime could be different. So this is the way the picture looks like in the simply connected space. Okay, so you're going to then choose, then you're going to pick 2 paths. Let's call them fx and fx prime. And these are going to be paths in x, which start at x0, and they go to x and x prime. You're going to do that for each of the 2 points. And the way this alpha map is then constructed is you're going to have to take both of these, you're going to have to project them to the quotient, and then you have to lift, and you have to show they give you the same answer. Now, notice that we have an x and we have an x prime, and there is no homotopy anymore between these two. This is where things get a little bit more difficult. But you can construct a path from x to x prime. So now you're going to construct a path f. This is a path in x from x to x prime. So you're going to pick some path over here. I'm going to call it f from x to x prime. So then we have the following relationship, that if you do fx and then you juxtapose, then you follow it through by f, that would be homotopic to the path fx prime. So this is the homotopy that you have, because you can see fx prime, that's the path from x0 to x prime. This is the path from fx and then followed from x to x prime. So this juxtaposition is a path from x0 to x prime. So this one is then homotopic to that one. Okay, so what do we do next? So here's the next thing that we do. So thus, if we project to the quotient, we would have that fx bar juxtapose f bar is homotopic to fx prime bar. Okay, this is what we have. And now what you need to understand, and this is like this is now, this square represents the quotient. Okay, this represents the quotient. So this is going to be x0 bar. This is going to be x prime bar. And actually, because x prime and x are the same mod h, they are also the same mod g. So they will coincide into the same point. So this is going to be x bar, which is the same thing as x prime bar. You're going to have a path going like this, fx prime bar. You have another path going like that, fx bar. And now, what was a path, these two come together, and you get a loop over here, f tilde. Okay? You're going to get this loop. So now observe that fx bar and fx prime bar are paths in the quotient. However, the other one, but f bar, is a loop in the quotient. Maybe more specifically, this is a loop that is based at the point. So this is a loop. So it's pi 1 x mod g, but it's not a loop at x0. It's going to be a loop at x bar. It's just at a different point. But other than that, it's the same idea. That's going to be a loop. Now, here's really the most critical idea. This is perhaps the most important idea. So the most important idea that makes this work is that f bar is actually an element of this, of the fundamental group of Y. It's just at some other point. I mean, I do not want to write down what the point is. That's kind of missing. It's kind of missing the whole idea of this. So why is that? Okay, so why? So let me go back to this again. I know I mentioned this before, but because it's so important, this is really what makes the whole thing work. I have to kind of go over this again. So we have that Y is, we have a covering map from Y to X. I know that previously I said from some point to some point. Let's not write the point over here. Just want to focus on the simple idea. You have a covering. So the fundamental group of Y, again, at some point, does not really matter, is a subgroup of the fundamental group. And I'm sorry, this is not X, this is X mod G, of X mod G at some point. And we said that the fundamental group is isomorphic to G. So it's isomorphic to G. Now, let's recall how this isomorphism over here works. So the way that it works, So the mapping is, if you give me, right, if you give me a point, right, you give me some point, you're going to translate that point by some automorphism. You're going to translate that point using some automorphism, right? So whatever that point that is, you're going to take G, you're going to apply it to that point, you're going to translate it to, and this gives you a path, right? So this is a path, and then you're going to take the path, you're going to project this path down to X mod G. So it becomes a loop, because the point and its translate, they coincide, and they will give you a loop in the quotient. This is exactly what we're doing right now. Notice that we have a point X. We took that point X and we translated. But what are we using? We're using this H. We're using something that's coming from this subgroup H. So we're translating, we're moving this point by using this H. So now if we take that path and we project that path down to the quotient, we get a loop. And because the translation that we used was coming from the subgroup, it will therefore correspond to some element in the fundamental group of Y. So it's actually, it's the one that, you see, this one corresponds to that subgroup. So it corresponds to that subgroup. And now, remember what we said earlier, that if something is if some element belongs to the subgroup, it means it lifts to a loop. In general, a loop will lift to a path. But because this F belongs to the subgroup, it lifts to a loop. So i.e., so F bar lifts to a loop in Y. So now let's draw so thus, if we lift, we have Fx tilde. So Fx tilde, this is the lifting of this one. That's the lifting of the other one. And that's going to be homotopic to the lifting of this one. So now you just lift these. So you lift this one, so it's going to start at y0. You're going to get a path. This is Fx lifted. You're going to get another path, Fx prime lifted. And now, this is the important idea, that this is a loop. This is a loop at some point. Doesn't really matter what point it is, but this is a loop. So it cannot, when you lift the red one, it cannot go like that. That's not a loop. It has to lift to some kind of loop. So it has to lift to some kind of loop, which means that the lifted path, its endpoint, has to close up at the same one, because you have a homotopy. It has to close up. So this shows that the endpoint of Fx tilde has to be equal to the endpoint of Fx prime tilde. But this is exactly what we call alpha of x, and this is exactly the way we define alpha of x prime. And look at that. If x and x prime are related to each other by a translation in that subgroup that corresponds to the cover, then alpha will be the same on those two elements, which shows that this mapping is well defined. And then from that point on, the rest of the argument goes through, and that completes the proof of this classification theorem. I would like to finish on one last issue about this topic, and this is the question of, is there a way to make this, let's say, classification theorem more general? So we are assuming, and this is the special case, that, so we are determining the coverings of a space of the form X mod G. So we are assuming that the topological space that we're dealing with you start off with a simply connected space, and then you quotient it out by some group of automorphisms, and we're classifying all of the coverings of the space. And the coverings of the space are determined by the subgroups of that G. That's basically what we've proven. But you can ask, what about being more general? So by more general, what we mean is instead, we have a space Y in general. So we do not assume that you're starting with a simply connected space and you quotient it out. So how can we find all coverings of Y? How do we do that? It's actually very simple. So you're going to calculate the fundamental group of Y at some point. Okay? So this is going to give you a group. Right? That's going to give you some kind of group. And then it can be shown, and it's a similar proof, but it's obviously going to be more complicated. So it can be shown that all coverings correspond to subgroups of this fundamental group. So instead of using the group of automorphisms, you just use the fundamental group itself. Now this is going to be a little bit trickier because what group do you have to use? Like previously we used a group of automorphisms, so what do you do here? So the idea here is that this is a space and it has a universal cover. So it has a universal cover. So assuming that Y satisfies the assumption that it's semi-locally simply connected, then it has a universal covering space. So you bring everything back to a universal covering space. And then you can ask, can you replace this space by X mod something? Is there a way to do that? And the answer is yes. Can you reduce everything back to quotients? There is a way to do that. We're not going to discuss it, but you basically what you do is you're going to consider, I'll just give you the simple answer. So you have the simply connected space, and you have this covering, and you're going to consider automorphisms from X to itself that make this diagram commute. Actually, let me remove this. You're going to consider automorphisms from X to itself that make this diagram commute. And these are called the deck transformations. So basically, this is the way you do it. You start off with a space that has a simply connected covering, and then you can consider automorphisms that keep this diagram fixed. And that's called the deck transformations, or the deck automorphisms. And then that is the subgroup of automorphisms that you're going to use to quotient out. So you sort of reduce the problem back to the special case. But we're not going to talk about that. We just do not need that. But if you're interested, you can look this up in the Breton book. He gets into details about this more carefully. So we'll just finish it right here. And I think we said enough on this topic.